Elimination Hydride Nucleophiles. So we've got a little review up there. We took our ketone and we added sodium borohydride. It adds the hydride to the electrophilic carbon. So our hydride's coming in as the minus. We've got our electrophilic carbon there. So the H minus attacks, the electrons would go up. We'd have a negative oxygen. Where does the negative oxygen get its electrons from? Or sorry, where does it get the hydrogen from? From water. Gets it from the hydrogen, so in a step 2 it would pick up the hydrogen and we'd have our alcohol. So it does a reduction of our ketone. 2-step mechanism, which I'm showing as 2 colors in the same drawing, right? Well, in this new chapter, we're now, instead of looking at ketones and aldehydes, we're looking at acid derivatives, okay? It's an acid derivative, which I think I've been saying, but I don't think I've explained why. We've got the carbonyl of an acid, and then our acid itself has that OH out there. Well, that OH could act as a nucleophile. Fair enough, yes, it could act as a nucleophile. Typically not. Acid would be the H. I'm asking about the OH. Leaving group. So when we talk about acid derivatives, really what we're saying is we're taking the acid functional group, and instead of it being an OH, we're changing it to some other kind of leaving group. So in this case, a chloride. So here we'd have an acid chloride. Okay? So when we switch up our functional group, how does that change the chemistry when reacting with our sodium borohydride? Officially with this, we would, yes, still be in water. What does the sodium borohydride produce? Hydride, so H minus. Okay, so there's our reactive species. What does that H minus need to react with? What should react with a negative? A positive. Okay, if we now want to add words on top of that, the positive species would be accepting electrons from something else, so it would be an electrophile. So where's there a positive atom?
The carbonyl carbon.
Our carbonyl carbon is our positive. So the hydride can come in, nucleophilically attack. The weakest bond to break would be the pi bond, so we'll shuttle those electrons up to the oxygen. The result is we will have added our hydride. We'll have our oxygen with that lone pair as a negative, and then we still have the chloride there. Okay. That carbon is not particularly happy with those 2 very electronegative elements attached to it, so it's going to want to attract electrons back. Where does it get the electrons from?
Chlorine.
Okay. So the suggestion is that we take the electrons from the chlorine and donate them in.
Sorry, wrong way. We get it from the oxygen and chlorine.
We get them from the oxygen. The electrons come back down. That would exceed the octet on our carbon. So we'd have to kick out some electrons. What electrons do we choose to kick out? The chlorine. Okay. If we do that, excuse me, we would end with our chloride with the negative charge. We'll have neutralized that charge on the oxygen, and we'll have placed the hydride on there. I do want to address Rob's suggestion, even though he's backed out of it, which is okay, of the chlorine donating electrons. Okay? That is absolutely still fair game, and you should be considering that. The electrons come back in, right? Okay, that would mean we'd form a pi bond. We'd exceed the octet on the carbon, so what do we need to do? Kick something out. What would we kick out?
The oxygen?
Okay. We could kick out the oxygen.
No. That would be 2 negatives.
That would be O minus 2. Is that a good thing? No, so that's a bad thing to kick out. What else could we kick out? the hydrogen. That would be H minus. Is H minus stable? No, it is at least going into a system that was already there, so that's a possibility, but that's not particularly stable. Okay? Or could have kicked out carbon. Are either of those or any of those three good leaving groups? No. Okay? So it's not that the chlorine can't donate the electrons in. It can. But what happens if it does that? Bad things. Okay? So what we're trying to do is think about what does it mean if we do these actions? Because if we get used to those actions, we can start to predict things and say, oh, that was a bad idea. I shouldn't have done that. And now I can backtrack and say, well, what else? What else could have helped that carbon out? I could have gotten electrons from the chlorine. That ended in bad results. I could have gotten electrons from the hydride. Okay? Take the electrons back from that. Okay? Would that have worked? Okay? We'd get H plus and we'd get a negative carbon near two sources of electrons. And that's probably not a good idea. Okay? So where's the best place to get the electrons? Our oxygen lone pairs. Okay? Why else should we be zeroing in on the oxygen as our lone pair electrons for this? It's the most reactive thing there. That carbon may be unhappy with two electronegative elements attached to it, but it's the oxygen that's driving that chemistry. It's a negative oxygen. Stabilize the negative oxygen. Stabilize that negative oxygen by having it share electrons with the most positive thing. The most positive thing is going to be that carbon. Does that make sense? Okay. So if we start with the acid chloride, what are we saying our product is? An aldehyde. What's still in solution? Sodium borohydride, so there's still hydride in solution. Why does that become problematic?
Because it's going to attack you.
Aldehydes react with sodium borohydride. So it'll end up going through and repeating the reaction to take us down to the fully reduced or the mostly reduced alcohol state. Okay? So the reaction continues. How do we know the reaction continues? And we've addressed some answers that explain why the reaction continues, so I'm just asking for you to repeat some of those.
After that one's formed, you still have the negative hydrogen, and then you have an electrophilic carbon.
Yeah. Okay. We've done reactions before where we still had electrophilic carbons. Okay, everybody's favorite. We can pull up this one. Oops. If we ran this reaction, we get the substitution, right? And it stops after one play. What happens if I change the conditions and I switch to Br2 but hydroxide? What happens?
It cascades.
It cascades and I continue to get reactions. Okay? Well, why? Why did one case the reaction continue versus one case the reaction stop? Okay? You change the conditions. Okay? So that's an explanation for why. But why is changing the conditions matter? We look at our mechanism and say that once we've done one substitution here, the slow step of this reaction is that hydrogen reacts with the oxygen. So we're saying our oxygen is basic. If we look at the product in red, right, and compare that to your starting material, the product in red is less basic than the starting material. which means under acidic conditions, I'll only get one bromination because I produce a material that is less reactive than I started with. Does that make sense? When we shift to the purple one, our slow step is the removal of the hydrogen. Okay? So we're saying the starting material, in comparison, we'll go backwards to the red structure, okay, is about acidity. Okay? The red structure is more acidic than the purple structure. Why?
The bromine.
The difference between these two structures is that there's bromine versus not. What does that bromine do to the acidity at the alpha position?
Increases.
It increases it by what process?
Induction.
Induction. Under basic conditions, the very first product that I make is more acidic than my starting material, so the reaction cascades. Does that kind of make sense? Okay. So what we're looking at is not just, well, we know it happens, okay? And we can make that argument with our reduction process up at the top. Okay, we know aldehydes react with sodium borohydride. Okay? But what we could start to do is consider what is the reactivity of that intermediate product versus the starting material. Okay? And in this case, it becomes a little bit more complicated because if we compare across, the chlorine has electrons, right? What could those electrons theoretically do? Resonance stabilization of the carbonyl. Whereas the aldehyde doesn't have that, which would mean what about the aldehyde's reactivity?
More reactive.
We could predict it to be more reactive. Because our intermediate product is potentially more reactive than our starting material, what should happen? It should continue to react. If your product is more reactive than your starting material, the reaction should continue. Okay? This one becomes a little bit tricky because aldehydes are actually less reactive than our acid chlorides. Okay? Why? Why were we saying the aldehyde is more reactive? What was the thing about our acid chloride that we're saying, oh, that makes it stable? Resonance. Chlorine donates electrons in. How many bonds would the chlorine have? 2. How many times do you like seeing chlorine with 2 bonds? No. In fact, that's a super rare circumstance. That resonance contribution is insanely weak. And really what we end up seeing is an inductive withdrawing effect due to the chlorine. Okay? So the explanation for why this reaction continues on, unfortunately, is going to fall back to, we know it does because we studied that in chapter 17. Kind of, sort of? Okay. But what happens if I change the acid chloride to a different material?
Like what?
What if I change it to an ester? Is that going to change the reactivity?
Yes.
Well, the acid chloride versus the ester are drastically different things. So yeah, that could very much change the reactivity. Okay? How does it change the reactivity?
I mean, the reaction is still going to do the same thing.
Your oxygen has resonance.
The oxygen has resonance, which means what happens to the activity of that electrophile?
Less reactive.
Becomes less reactive. Okay? If we compare our aldehyde to our ester, the aldehyde is certainly more reactive. So if that first step happens, what would we expect to happen? It should keep reacting. Does that make sense? Okay. Remember, the phrasing there is very, very important. So I want to walk through that again. I said if that first step happens, then the second one should also happen. Okay, why does that become important? Does the first step happen? Okay? That decision is ultimately going to come back to experimental testing. Okay? And that's looking at the relative reactivity of all of these species in comparison to each other. If we go through and compare the acid chloride to the ester, not to give too many things away, to the ester, to an aldehyde, which one's the most reactive? The acid chloride ends up being the most reactive. Okay, why? We don't have that resonance effect, and it ends up being primarily induction. Well, the aldehyde doesn't have that induction. There's no resonance to stabilize that. So you're right, the aldehyde becomes very reactive, but it doesn't have that inductive withdrawing effect. So the acid chloride should be more than the aldehyde. Should the aldehyde be more than the ester, or the other way around?
Yes.
Yeah, why?
Because of the resonance effect for the ester?
The ester has this resonance effect. So we see 1, 2, 3. What does that mean for this reaction now? We know sodium borohydride reacts with acyl chlorides. We know it reacts with aldehydes. Do we know if it reacts with esters? We haven't clearly established that. According to our ranking of reactivities, the ester is the bottom of the pile. So we're now shifting to a functional group that is less reactive than everything else. How do we know if it actually reacts or not?
You test it.
You have to test it. Okay? And we've kind of alluded to this throughout the semester, but a lot of what you study has already been tested, and you're being asked to memorize those results. We can come up with patterns to help you explain why one is more reactive than the other. But eventually, it's going to come to a line. This is the line where that reactivity changes. Okay? Esters don't react very well with sodium borohydride. Right, and we'll address that in a second. We'll actually look at an image of it. But what if I still want to convert the ester into the alcohol? What could I do? You're suggesting lithium aluminum hydride. Why? Lithium aluminum hydride does the exact same thing as sodium borohydride. And as we addressed back in chapter 17, the lithium aluminum hydride is a stronger hydride nucleophile than the sodium borohydride. Okay? Both the lithium versus the sodium comparison and the boron versus the aluminum comparison. Right? So if I want to reduce the ester, I would need to switch to lithium aluminum hydride, or LiAlH. Okay? This does change the solvent, because LiAlH is so much more reactive that what do I need to ensure is not present? Protic solvents. So I can't run that in the presence of water. Where do I get the hydrogen to ultimately protonate the alcohol? It has to be an H+.
Do a second step workup.
Second step. So the LiAlH changes to now being 2 steps. Okay, kind of makes sense? Now our reaction progresses. We sort of, kind of? Okay. We already talked about all that. So our difference between sodium borohydride and lithium aluminum hydride. Cardi's got a pretty nice image that goes through and ranks our acid chloride, anhydride, ester, acids, and amides. Okay? In the exact order, by the way, that matches the energetics of those starting materials. The acid chloride is the highest in energy. The amide was the lowest. Wait, was it? What was lower in energy than the amide? C000 minus. So C00 minus a carboxylic acid that has lost its hydrogen. It's known as a carboxylate. Okay? So yeah, that would be the lowest. Okay? But he's got all of the other ones ranked, and it shows those reactions. And if we go through and look at them, you'll notice that there is a difference here. For the carboxylic acid and the amide, we don't see a reaction. Okay? So the sodium borohydride does not react with those. Didn't I say something about esters, though? Didn't I say that doesn't work very well? It's showing it works.
Very slow.
It works very, very slowly. Okay? So that is not a good reagent to pick if you're trying to reduce out an ester. Okay, does that make sense? And so that's what Cardy's trying to do within this. Next thing I kind of want to draw your attention to, if we look at the reaction, acid chloride, actually let's take a step back. If we look at that reaction here, what happened? What kind of reaction is that? From the acid chloride to the aldehyde. Okay. Substitution. What are our mechanisms for substitution?
SN1 and SN2.
So which one happened, SN1 or SN2?
SN2.
Neither. What happened?
You added something and you eliminated something.
I did a nucleophilic addition followed by a nucleophilic elimination. The net result, looking beginning to end, looks like a substitution reaction. Okay? This is something that you could get tricked on the ACS, and they could throw reagents at you and be like, well, what mechanism is it, SN1 or SN2? You're like, oh, it's substitution. Well, I don't know. Let's pick one. No, it's a strong thing, so it must be SN2. With the carbonyl, you're not doing a substitution mechanism. Okay? You're doing a substitution reaction. Does that make sense? It's a bit misleading. How about the next one? Elimination?
Reduction.
Okay, I'll accept reduction. Right? That's not technically one of our, 5 reactions. So I don't quite accept that. But reduction is true. We did reduce the carbonyl. What kind of reaction?
Nucleophilic addition.
We did an addition. What did I add in the process of doing that addition?
2 sigma bonds.
A nucleophile is what started that addition. So the mechanism is a nucleophilic addition. The reaction is just an addition. Does that make sense? Okay. So to go beginning to end, what have we done? We did a substitution, which is all sorts of weird because it was a nucleophilic addition and an elimination, followed by an addition. So we did 2 additions and an elimination, beginning to end. Does it look like it was just a straight substitution? No. Why point this out? What is Cardy calling it?
Substitution.
A substitution. Okay? So the language can be confusing because you're looking at different aspects of those puzzles when you're putting it together. Does that make sense? Okay? So be a little bit careful with that language. Recognize what's happening. Think about that mechanism. Nucleophilic addition, followed by elimination, followed by a nucleophilic addition. Okay? Kind of good? Okay. Lithium aluminum hydride, because it's so much more reactive, does them all. Okay? It'll do the full reduction.
With the anhydride too, it looks like it reduces both parts.
It reduces both parts.
They're different.
What do you mean? Where?
The stuff in brackets.
Yeah, 2
Okay.
carbonyls.
So if we go to the stuff in brackets, okay, so what you're zeroing in on is important. Okay, and I need to be careful with what I erase. So let's go through and just look at that so it stands out. Sodium borohydride takes you to a primary alcohol, and your leaving group is a carboxylic acid, right? If we look at lithium aluminum hydride, what happened?
That's primary alcohol.
You get 2 alcohols. Why?
It reacted with both carbonyls.
Lithium aluminum hydride is so reactive that it will react with our carbonyls. And it does a reduction. What's the leaving group? Carboxylic acid. Do carboxylic acids react with lithium aluminum hydride? With lithium aluminum hydride? Yes. That's why we're seeing that extra reduction. Okay? It's easy to swap them. Okay, does that make sense? So it's just continuing to react with the carbonyls. Other things you note?
Does the Li and LiAlH react with the carboxylate?
So that's an interesting question. What do you guys think? So you'll notice it's not on the list.
So I think
Okay, so if we drew this all the way at the bottom, there's our RO minus. So that is the lowest instability. If the amide and the carboxylic acid don't react with the sodium borohydride, that's not going to react with the sodium borohydride, right? So the question that you asked was astute. Well, you didn't ask about sodium borohydride, you asked lithium aluminum hydride, right? Should that react? Lithium aluminum hydride goes in 2 steps. Why?
because if you have the solvent with it and it's aprotic, it's going to attack it.
Getting at the right idea, if you have the solvent with it and the solvent is protic, the hydride will react in an acid-base reaction with the positive hydrogen from our solvent. Okay? Absolutely fair game. Should the carboxylate react with lithium aluminum hydride? Okay? It's even less reactive. Okay? The answer to that is actually already up on the board. What's the reactivity of that functional group?
It's an acid.
For those of you at home, in purple. What's the reactivity of that functional group?
The H plus, or the H, that will become H plus.
It's an acid. You mean it's protic? Yeah. If it's protic, what's the very first thing the lithium aluminum hydride's going to do?
That hydrogen form.
React that hydrogen, which then means
Carboxylate.
we would have a carboxylate. What product do we get?
Primary alcohol.
We do get the full reduction. Why?
Because when you put the acid back in,
The very first step is we remove the hydrogen to make the carboxylate. Right? That's the very first step of that reaction. This says we form an alcohol. What can you tell me about the reaction up top, the red one? What do you think? Does that one work?
Yes.
It has to. It has to work because that's why the carboxylic acid is getting reduced. Okay? So it would beg an interesting question. We said that we don't want a protic solvent because it kills the nucleophile. But our starting material is protic. What would that do to the nucleophile? It would kill the nucleophile. If there's no nucleophile, how the hell does it do the reduction?
Excess.
There's a lot of the nucleophile. Okay? Solvent is in a huge concentration. Okay? If you think back to 152, water was never included in your equilibrium expressions. Why not? That's a hard question. Water's not included in your equilibrium expressions, not because it's a liquid, but because the concentration of the water through the course of your reactions doesn't change. So you can treat water as a constant and group that into your equilibrium constant. So solvent amounts are so high in comparison to your starting materials that the solvent would undoubtedly completely remove all reactivity of our hydride nucleophile. The carboxylic acid is not acting as a solvent here, it's the reagent. Which then means the amount of that acid is
less.
very, very small. Which means I can account for that acidic hydrogen by adding an excess of the lithium aluminum hydride. Some of it will go through, remove the hydrogen, get me the carboxylate. I will still have leftover lithium aluminum hydride that can then go through and do the reduction the rest of the way. Okay? What makes that extra interesting is O minus a good leaving group? No. So how the hell is it leaving? It's coordinating to the aluminum. So we end up creating an aluminum oxide leaving group, and that's what's facilitating that loss. Why does it not work with the sodium borohydride? The boron-oxygen bond isn't as strong, so it can't pull that off. Okay? So good question about the carboxylate. Yes, carboxylates will react, and we see that in the carboxylic acid. Kind of makes sense? Okay. So, why barely acids? Okay, for sodium are barely esters and not acids and amides. Fudge, I can't say that word.
What word do you say?
Amides, it took me a little bit. So why does sodium borohydride barely react with esters and then not react at all with the acids and the amides? Would it help if we drew out a structure? There's an ester. Okay. Why does it not react with the ester? Your electrophile is less reactive, is less positive. Okay? And then it doesn't react at all with acids and amides. Well, what do the acids and the amides have in common?
Resonance electrons?
They still have those electrons. Those electrons are still doing resonance. Right? So both of those are going to be less positive. Why would the amide be even less reactive than the acid? Nitrogen's less electronegative. It can share even better than the oxygen, making that carbon even less positive. Why is the acid less reactive than the ester?
The carbon attached?
I see where you're going. You're referencing this carbon attached. No.
You said why is the acid less than the ester?
Why is the acid less reactive than the ester?
Um,
In a nucleophilic addition.
In a nucleophilic addition, the hydrogen kills the nucleophile, and then you end up with strong resonance.
So it's good to point out the differences. Okay, so you went to the ester and noted that an ester had that carbon. Unfortunately, that carbon isn't really doing much. To get an idea of why it doesn't really do much, you're looking at effectively an alkane. How reactive are alkanes? Not really. So the other difference would be looking at that hydrogen. Is that hydrogen reactive?
Yes, it's acidic.
It's the hydrogen off of a carboxylic acid. That is an acidic hydrogen. While sodium borohydride can work in protic solvents, acidic solvents are a slightly different system. Okay? Those acidic systems are now going to react and quench the nucleophile, giving you the carboxylate, which is even less reactive. The carboxylate's not going to continue forwards. Does that make sense? So what we're kind of nuancing is the difference in reactivity across all of these. Does that make sense? Okay. Oh, I was wondering where this was going to show up. What we see here really deserves to be on its own slide. Okay. What we're addressing is all of the carbonyls that we've talked about this semester. Okay. We've got our aldehydes and ketones. What do we have at the top? Yeah, the acyl halides or acyl chlorides. Specifically here, chlorides, the one underneath.
Esters.
Anhydride. It's an anhydride because you have two carbonyls. The ester shows up down below. Ester and acid, then amide, and then our carboxylate. What are we showing by putting this on a slide?
Reactivity.
The reactivity, okay? The very top is our most electrophilic. That is an exceptionally high energy electrophile. As we move down, we're dropping in energy, okay, making it progressively less and less reactive. What I find sometimes misleading about the chapter divisions here is that we talk about acid chlorides, or acid derivatives, which means just those. And we tend to forget that we also talked about other carbonyls, aldehydes and ketones. Where do the aldehydes and ketones fit into that reactivity? Well, they sit above the esters because they don't have the resonance. They sit below the anhydrides because
they don't have the resonance.
They don't have that inductive withdrawing effect or a counter resonance effect, if you will. Okay? So if we can remember to keep this list as far as our sequencing of reactivity, this can help us differentiate between it and see those reactions. Man, there's something just dying in there.
Don't die.
You're not that lucky. Yeah. If we look at the staircase, that ladder thing that we had, you'll notice that the aldehydes and the ketones weren't on it. Okay? Why not? Because the aldehydes and ketones weren't being interconverted at that stage. We weren't concerned about that. Does that make sense? So we're seeing information show up in a variety of different locations. I just want you to remember that content. We good? Okay. So what would you expect here? Say that again? Okay. The carbonyl reduces out to hydrogens. Sorry, the structure was a little bit more complex. Couldn't just draw it from my memory. Okay. And you end up with the amine. Some people tend to struggle with this reaction because if we go back, I think I'm going to regret this. Yeah, I'm going to regret this, damn it. If we go back, we look, what do we end with? Alcohol. 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 Okay? So if you just remember, we reduce out to get alcohols, you're stuck up a creek. Okay? If instead you memorize, what did you do? Or did you just, you're that good? I'm fine with either.
Just saw your slide.
That's fair. Okay. Saw the slide in advance. What could we memorize to help us? Instead of going primary alcohols.
The slide where it just...
Oh, where it said the amine. You just remembered it that well? Dang. Okay. That's fair.
Okay, yeah, I remember it though.
What's actually happening is you're reducing that carbonyl and then leaving whatever.
When we're thinking about the reaction, what you're doing is reducing away the carbonyl. Okay? So if you want a cheat for memorization on this, get rid of the carbonyl. Okay? Where that can become problematic is if we start to go through and label things. And I do something like this. Blue oxygen versus red oxygen. Here's my product. Is that oxygen blue or red?
I don't like that. You did that wrong.
Yeah. No, I didn't.
It's red.
Is it red or blue?
Come on, man.
Okay. If we go with our memorization on the process, we just reduce away the carbonyl. Okay? If that's the case, then we would say that oxygen must be the red one. It's not what we do, though. Okay? It's not just a reduction away of the carbonyl. you have to consider the mechanism behind that. Your hydride comes in, attacks, kicks up, electrons come back down, we eject the red one. Okay? So the oxygen remaining at the end of that reduction ends up being a blue one. So they can ask a mechanistic question and say they wouldn't ask it with colors clearly, okay? But we could switch it up. They won't do it with shapes. But we could say oxygen 18. What is oxygen 18?
Blue oxygen.
It's an isotope.
Touche. It is the blue oxygen. Where does oxygen 18 end up? Okay, and so what they could do would be show that structure. They could also, not that one, my bad. They could show this one. And they say, well, which of those should have oxygen 18 in it? And what they're asking is, do you know the mechanism? If you don't know the mechanism, and you've just memorized just get rid of the carbonyl, you'll start placing that oxygen or that red oxygen or radio-labeled oxygen in a different place. Oxygen 18 is just heavy oxygen. Okay? We can tell the difference.
I don't know what looks on the side though.
Which?
The one that had the
Yeah, but they aren't labeling which oxygen is which. They haven't color-coded it. And so that's the issue that I'm pointing out. They haven't color-coded that. It just looks like it's straight across. They aren't addressing where the oxygen goes. Okay? So you have to be careful with tracking where that oxygen goes to or ends up.
So you can eject that ethanoate because the oxygen is negative enough, but in that amide, you can't eject the amide because nitrogen is not comfortable enough as a negative.
So, and this is where the question would come in. If we go through and run the mechanism up here, our hydride attacks, we get up to this intermediate. Right? In the case of the ester, oh, I can't believe I'm sticking with this stupidly large structure. The hydride comes in, attacks, kicks up. Right? What happens with the ester?
Electrons come down from the oxygen.
The oxygen comes down and it kicks out
The other oxygen.
the other oxygen. What happens with the amide?
Is that coordination you were talking about earlier, or coordinates with aluminum?
If the amide follows the exact same mechanism, what do?
You created negative.
We would kick out the nitrogen, which would mean we'd be ending with a primary alcohol, not the amine. So the nitrogen doesn't get kicked out. What happens? The oxygen gets kicked out. Why would the oxygen get kicked out?
Because the nitrogen pushes its electrons in?
The nitrogen will preferentially push the electrons in, kicking the oxygen out. Why?
Because nitrogen is less electronegative.
Nitrogen is less electronegative than the oxygen, so in this situation, in this intermediate, the nitrogen is the one making the pi bond, ejecting the oxygen. For those of you saying O-2 is a horrible leaving group, abso-freaking-lutely. But remember, you've got the lithium in the aluminum that can coordinate to that oxygen to stabilize it. Okay? And that's where these mechanisms become weird, particularly when you move into the amide and the acid, the amide and the acid, is you end up ejecting an O-2. Okay? You aren't ejecting O-2. What you're ejecting is oxygen coordinated to lithium or aluminum. That is your better leaving group. Does that kind of make sense? So you have to have that secondary piece. Yes, sir.
In showing the mechanistic step, would it be a good idea to show that, or is it required to show the coordination onto the oxygen and then the ejection?
In a mechanism, that's a good point. I've never asked the question. And I don't think I ever will because I don't want that coordination really be drawn out. I'd rather you just kind of remember that overall.
Coordination occurs and that's why this is valid.
Yep.
Okay. And is there, if you had, say, no, I suppose that was wrong.
What do we produce after this step?
Primary, well, yeah, and
What do we have?
pi bond,
And in particular, what kind of pi bond?
pi bond.
A polar pi bond. And what reacts with polar pi bonds? Lithium aluminum hydride. Now your secondary reduction happens, where it's just a nucleophilic addition.
You need acid work.
The acid workup would happen, and actually in this case, no, we won't need an acid workup because
Because it's coming in, you've got a positive nitrogen, the negative H comes in and kicks it in, fixes all the, neutralizes.
it neutralizes all the charges. If we had a primary amine, then things become a little more challenging. Okay, but when it's fully saturated with carbons,
Okay.
we don't have to worry about it. Okay? So, how about this? I have an acid chloride, but I want an aldehyde. If I throw sodium borohydride at it, what happens?
Reduces.
It reduces to what? Primary alcohol, so not an aldehyde. So let's throw lithium aluminum hydride at it. Also all the way down. So that becomes a problem. How could I convert the acid chloride into the aldehyde? Okay? The only thing that really needs to happen there is I need a hydrogen instead of a chlorine. That hydrogen has to come in as a negative charge. All we've really got is lithium borohydride or sodium borohydride or lithium aluminum hydride. So how could we do that? Okay, next one, ester to an aldehyde. That one becomes extra weird. Why is that one extra weird?
Because you have to maintain that pi bond. You can't play around with that.
Yeah, the pi bond, but arguably that pi bond's not a big deal because non-polar pi bond versus a polar pi bond. Why is this one extra weird? Where's the reactivity of an aldehyde in comparison to an ester? Aldehydes are higher than esters. We're going up in energy as opposed to down. Okay? So both of these reactions are very, very bizarre. Okay? How could we possibly do it? We need a hydride in both cases. The question is, how do we get that hydride? Okay? How do we do it? Yeah. Okay? There are two sequences to go through. This top one, lithium, aluminum, hydride, tert, T-butoxide. Tert, T-butoxide. I'm not positive that's proper nomenclature, but you use that. Okay? Or in this bottom one, you use diisobutyl aluminum hydride. Okay? Yeah, I know. Don't stress. Okay? But what I want to do is address some of the kind of important characteristics on these. Let's take a look at the top one because we have that structure given to us. Where's the reactivity in that? We have lithium. What charge? Positive. We have the aluminum, which typically carries. Aluminum is a +3 typically. Okay? Then we have hydrogen. What's that hydrogen connected to? What's that hydrogen connected to? It's connected to the aluminum. That's an ionic bond, which means the hydrogen is negative. We have a hydride nucleophile. There it is. Okay? What's the rest of it? Okay. 3 negative charges, ultimately to stabilize and balance those things out. Okay? That big nasty reagent, the only thing that you need to recognize and see in there, in my opinion, is aluminum and H. And that aluminum and H is now an ionic bond, and because we know it's an ionic bond, that becomes H-. it now does a reduction. There's a nucleophile that can reduce carbonyls. Why the hell is it not lithium aluminum hydride or sodium borohydride?
Because those will reduce them
All the way.
Those do something very repetitive, okay, or very consistent. This one's doing something weird. So if you see a reagent like that, you can identify the chemistry, H-, now do something weird with it in the reduction. Okay? I don't expect you to memorize that. What I expect you to do is to recognize it doesn't fall into the standard patterns, but that the reactivity is H-. How could it possibly react? What is the most likely process for it to follow? Does that make sense? So you would be expected to look at that, be like, that's H-, that's a carbonyl, I need to do some level of reduction. If you did a full reduction, why the hell did we use that reagent? Why didn't we pick something nice and simple like lithium aluminum hydride? Eliminate an answer. Does that make sense? After that, you'll probably get all sorts of other weird answers. Right? I could foresee this showing up as a weird answer. Right? I had negative oxygens. Negative oxygens attacked the carbonyl. Is that the one that's reactive? No, the hydride's the more reactive. So what you need to be able to do is to kind of sift through those elements to find the thing that stands out as the reactive species and zero in on that, focus your chemistry there. Make sense?
If you switch reagents, would it still work?
Yes. Okay. What happens with the dibol? Or I don't know why Carty references it as diba. Okay. Nearly everywhere else I've ever seen it's referred to as dibol. Okay, diisobutyl. So there's isobutyl, aluminum. I need diisobutyl and hydride. Diisobutyl aluminum hydride is a little bit different than our standard reagents. Why is it different? No.
Aluminum's
You
alone?
don't have the lithium.
There's no-
I don't have a lithium. There's no positive ion. So more importantly, there's no negative. Okay? There's no strong hydride nucleophile. We're actually looking at that H- again being our reactive species. It's going to be the largest difference in electronegativity. That hydride's definitely going to be it. Okay? But this organization allows for a coordination between the oxygen and the aluminum so that hydride can attack to get you this system. Okay? If I'd saturated the aluminum with another bond, I don't have a slot for the oxygen to hook up as easily, and the reduction doesn't happen as cleanly. Okay? That one's trickier to evaluate. I would still argue it falls under the same category. You have aluminum and hydrogen, which means ionic bond, which means H-. Look at your answer choices. Okay? You're now adding an H- to that structure. If it was going to do a full reduction, we should have picked lithium aluminum hydride. If it was not going to reduce, we should have picked sodium borohydride. Okay? So it should be doing something in between that. Make sense? Okay? And ultimately, the explanations behind these go back to how those substituents change the chemistry of that aluminum hydride bond. If you remember back in chapter 17 when we talked about sodium borohydride and lithium aluminum hydride, I said we can change out those pieces to do different chemistries, but ultimately it's still that hydride that's the focus. That's what you have to find in these cases. And we'll change out those other pieces so that they attack different functional groups. Kind of, sort of? Okay. So what I would expect you to kind of memorize on this, the dibol is the one that really stands out. Okay? The dibol is typically referenced, probably because we've got this nice little acronym for it. Okay? Whereas that one, I don't think there's an acronym. Tritert. I was close. Okay? There's not a nice little acronym for that one. Okay? So if we were imagining writing an exam, which one do you think would show up on an exam?
The
diball because that's a hell of a lot easier to write than the other one. Okay? Which may seem silly, but you're now thinking about how an exam can get written. That's a good thing. Okay? The specifics behind it, they're both sterically hindered. This prevents that secondary reaction with the aldehyde because it's so hindered it can't coordinate in as easily. Okay? And they're both run in very cold temperatures. Okay? So we double back. Negative 75 degrees Celsius, negative 78 degrees Celsius. These are very, very cold. That cold can also limit that reactivity. Make sense?
Yes.
Yes. Okay.
Is there a difference between the 3 degrees Celsius? Or is it just like that?
That's just what solvent they picked to run it, probably. It's possible also there's a typo. Right? Because negative 78, I think, is
You have to avoid the solvent freezing.
acetone and dry ice. I think it's negative 78. Maybe it's nitrogen, actually. I don't remember. Might be liquid nitrogen. Right? So they're both run cold to limit that reactivity. The difference in temperature, I wouldn't stress about. Right? That's looking at nuances of the reactions. You typically don't need nuances. Okay? So recognize cold or hot. Okay? And again, pointing it out again, regardless, look for the metal hydrogen bond. When you see that metal hydrogen bond, you have a hydride, you have a nucleophile. Okay? Is it a standard default lithium aluminum hydride or sodium borohydride, or is it something weird? If it's something weird, do something slightly not normal. Slightly. Still keep the hydride nucleophile. Yeah? Cool. So, organometallic reagents. Where else could we get negative carbons? So what are some sources of negative carbons? Butyl lithiums. PPH3. Okay, you're looking at the Wittig reagent. Gilman. The other big G? Grignards. Okay, so those are some of our big organometallics. The the Wittig we typically don't see because the Wittig focuses on aldehydes and ketones, not our acid chlorides, okay, or acid derivatives. Man. So what would happen? If I take a Grignard, what's the reactivity in that species?
C minus. Negative carbon.
A negative carbon. So we could take that negative carbon and do what with it? Okay. Have it attack the carbonyl, our most positive spot. What happens?
Push electrons up onto the oxygen.
We break the pi bond. It's going to come back down. Notice that we're really doing these cheat mechanisms now because it's a lot of kind of repetition. That's okay. Do acknowledge that they are cheat mechanisms, right? We're all on board with that. They are definitely not valid mechanisms. What do you mean, wait a minute, what?
I mean, like, that's how it works. So red is step 1, blue is step 2.
Okay, that's not an official mechanism because an official mechanism needs to show the product of red,
Oh, okay.
then the product of the blue.
I understand the cheats.
Okay, so we good?
Yeah.
We'd eject our leaving group and we would end with ketone, right?
No.
What do you mean?
Well, I mean, we've got another, I'm assuming that you didn't have a stoichiometrically perfect amount and it magically only reacted once ever. You've got a polar pi bond there.
What is the reactivity of a ketone?
It's less reactive.
It is less reactive than the acyl chloride, but it's still pretty damn reactive,
And you're going to keep running down.
which means the Grignard's going to react again. Okay? So we would get a second nucleophilic attack, which would break the pi bond. Can we do another pi bond break? Or sorry, pi bond reform? Why not?
You don't have a leaving group.
There's now no more leaving group. So what happens?
Go to the process and do an acid work.
Now we'd have that second step of adding the acid to protonate. Okay? So our Grignards, very similar to our lithium aluminum hydrides, super reactive. They're going to add fully. Okay? Same with the alkyl lithiums, though you tend to see those a little bit less frequently. Any idea why?
Lithium's a pain in the ass to work with.
Sort of.
They're really, really reactive, so it's a great chemistry.
Okay? The difference in electronegativity between the lithium and the carbon versus magnesium and carbon is higher, which means that carbon is
Even more reactive.
that much more negative. Because it is that much more negative, it's going to react with whatever it can get a hold of as fast as possible. Which means the alkyl lithiums start to also increase their base reactivity. And so our alkyl lithiums tend to act as bases instead of as nucleophiles. They can still act as nucleophiles. We just have to be a lot more careful with the presence of acids.
With that, so it's just like avoiding water and acids.
Avoiding waters and acids, yeah.
Anything with an easily decarbonized hydrogen.
Yep.
So you could run that and anything with like a you just want to run alkyl lithium.
Alkyl lithiums with amides would be a bad idea. Yeah. So if we go through, Cardy's got a nice mechanism showing it all the way through. We just walked through that. We did it in 2 steps, right? 2, which was really kind of 3. If we break this down, we've got the same 3 steps. Remember, we threw on the 4th, and we didn't show that one. Okay? Make sense? Okay. So, if we switched it up and looked at these situations, what do you think?
I would say that for that one, you get basically a primary alcohol. The methanol flies away, and you would
Right, does everybody understand what he's saying? A primary alcohol. Everyone want to agree with that? Primary alcohol means you have
no, sorry, a tertiary alcohol with, they're not hydrogens anymore.
the Grignard attacks, not Grignard, the organolithium attacks.
Twice.
Break the pi bond, reform the pi bond, eject. We'd then have a ketone,
Which then reacts a second.
which would then react a second time.
And the H2O is there to
And then the H2O is our second step to go ahead and protonate our oxygen. Yeah?
that means lithium hydroxide.
Lithium methoxide.
Oh, okay.
Okay. What happens in the next one?
You get another tertiary alcohol.
We'll get another tertiary alcohol. Same deal. What the hell is this thing?
That's your solvent.
It's a solvent. Okay. Why is it there?
So you can't use a water solvent, otherwise it's a non-protic solvent, it looks like.
To confuse you.
Oh.
When you go through and look at a list of things, identify the most reactive thing. We've been talking about this as we go through. Find the most reactive thing. I don't care that that's really there. I can break that down and draw out the structure, and really what we've got is a pretty polar ether, and a large one. Why is it there? We're trying to increase the solubility so that these things can interact with each other. The chemistry is still focused at the negative carbon connected to that positive metal. Make sense? Okay. So zero in on where that chemistry is. Try to avoid those other big kind of pieces that float in there. Okay? Sometimes they're important, but it tends to be fairly rare. Okay? So in both cases, we end up with our tertiary alcohols. We end up getting 2 equivalents of the R minus. Okay? That can get phrased in a tricky question because we could say with this top one, a student wanted to go through and make a ketone. So they took the ester and they reacted the methyl lithium with it. They didn't get a ketone. What'd they get? They got a tertiary alcohol. Right? But the way the question is phrased is to try and to get you to go, oh, it just does once. Recognize the chemistry of all of your reagents, draw the pieces, and see what you get. Okay? Don't let particularly text questions mislead you. Make sense? Okay. What reagent are we adding in this time? We've got a Gilman. What was special about the Gilman?
Not as strong on carbon nucleophile.
Okay. Not as strong as our Grignards. So when we talked about Gilman, we really only addressed the Gilman as being a 1,4 addition and the Grignards being 1,2. Okay? And we never really addressed what this question is going to reveal. Okay? It is still a carbon nucleophile. So we're going to take that carbon as a nucleophile and go through and attack. We would break the pi bond. Then we reform the pi bond and we eject our leaving group. Okay? What would it look like at that point? Well, we should have our carbonyl formed. There's that first carbon. 2, 3, 4, 5. 2, 3, 4, 5. Pi bond, yeah? Everybody agree?
Yeah.
Okay. What are you suggesting, Lee?
2.
What do you mean 2?
Times 2.
Okay. So why are you saying times 2?
You still have a polar pipeline.
Okay, and this is an important thing because 2 shows up in a variety of different locations, particularly with this question, and that's why I'm really pushing on this. Okay, so I've got an argument that it's 2 because I still have a polar pi bond. Couldn't the Gilman attack the polar pi bond?
Yes.
Okay, so that is one place where 2 can come into this. The other place that the 2 can come in is up here, right, where it says 2. The Gilman has 2 equivalents of carbon nucleophiles because there's 2 carbons connected to the copper. Okay, those are 2 different. Those are an A and B of different meanings. I didn't need another 2. Okay, so the green 2 that we're referencing is kind of an artifact of what the Gilman reagent is. Okay, it will always have 2 carbon nucleophiles coordinated to it. How many of those carbon nucleophiles react is the second question that you guys are asking. Okay? Yes, we have a polar pi bond. So now the question is Gilman a strong enough nucleophile to do a direct addition? It is unfortunately not strong enough. Okay? So I don't see why not is a valid explanation. And I would kind of lean with you. It's a freaking negative carbon. It's connected to a metal, just like a Grignard is. But the difference in electronegativity between carbon to magnesium versus carbon to copper is different enough to weaken the strength of that carbon nucleophile. It weakens it so much that it actually will not do an addition to the polar pi bond. Okay? This is kind of alluded to when we look at our conjugate additions. Where does Gilman go? 1,4. It doesn't do the direct addition. Okay? What we didn't explicitly talk about, and we is an unfortunate statement, what I didn't explicitly talk about, okay, I apologize, is that Gilman is a weak enough nucleophile that it actually doesn't do a direct addition to carbonyls. Okay? It'll only do it when we have superactive electrophiles, like acyl chlorides. Sorry.
I thought with the 1,4 edition, it was a thermodynamic kinetic thing, so it can do both, but it keeps getting kicked out. Or is it just
Well,
when
and
it
ultimately
does-
that getting kicked out means that
what causes
it doesn't
to
stay.
have to- Okay.
So,
It's just, it turns
yeah.
into a leaving group rather than the L minus.
Yep.
Okay.
Okay. Does it work with the, you said it, anhydrides? I don't remember. Okay. What we're officially looking at right now, if we go through and look at it, what were the examples for the electrophiles that we're looking at? Acyl chlorides. Okay, so we're looking at a lot of the acyl halides. What will happen is we'll now bring in the anhydrides once we've kind of addressed all of our bulk nucleophiles, and so we start kind of leveling them in that way. I believe it will react. Okay, and again, it's establishing that line. Where's that line? It won't directly add to aldehydes or ketones. Anhydrides are higher in activity. I would lean towards it actually reacting. Okay. So what we've now covered is our acyl chlorides. Okay. So if you start with an acyl chloride, here's all of the nucleophiles that you can add to it and what ends up happening with them. Okay. Some of them we've directly discussed. Some of them I kind of left for you to go through and look at, like our alcohols. We'll actually discuss those a little. No, we won't. Okay. Actually, we did. We did already address that. When did we address that bridge and that bridge? And for that matter, that bridge and that bridge?
Isn't that either first semester or second unit? Right there.
It's on that. Okay. Those are straightforward nucleophilic additions, so they aren't a big deal. Okay, we aren't doing anything kind of fancy with those. The lithium aluminum hydrides, the weird goofy one there, and our Grignards and our Gilmans are a little bit stranger, so we talked about those in a little bit more detail. Okay? But this is kind of our spider diagram, if you will, for our acid chlorides. Okay? The thionyl chloride, chapter 10. Reverting from the acyl chloride to the acid, we just need water. Okay? So that's all of our reactions. We've got our inner conversions on here. The inner conversions are important to have memorized, so you should be working towards that. If you need something to just start memorizing reagents, this type of summary slide shows up, I think, 2 or 3 times through the lectures. Okay? Starting with our acid chlorides, then anhydrides, then esters. Okay? And I don't think we look at the amides or the acids. Why? They're at the bottom of the food chain. Okay? So it's harder to see where their reactions are going to go. Okay? Oh, we'll briefly talk about it. Our sulfonyl chlorides, you actually already saw this. We're starting with an alcohol, and we're reacting it with toluene sulfonic acid in this case. Okay? What happens? The oxygen attacks the sulfur, we break the pi bond, we eject the chloride. That is the exact chemistry we're talking about right now, right? When did we talk about this reaction?
Chapter 10.
This is chapter 10. SOCl2 to RCl. It was the conversion across into a chloride. Okay? We could do it with the toluene sulfonic acid so that we had a good leaving group so that we could do reactivity. Okay? It was in chapter 10 because it was a useful substitution. It converted the OH to the chloride. Was it a substitution mechanism? No. Not at all. Okay? And when we talked about it in chapter 10, I was like, this mechanism doesn't belong in this chapter. It actually belongs much later in the semester. Ta-da! Okay, here we are. Okay, but it's again coming to what was the content trying to be addressed. In chapter 10, we wanted the end goal of a substitution. The way we got there, Cardi just kind of hand waved, was like, oh, this is what it is, and just kind of let it ride. Okay? Other kind of sulfur compounds are shown up at the top. All of these are pretty good as electrophiles, so we can have them react with our oxygens, okay, of alcohols or where else do you see an OH? Carboxylic acids. So these three structures work out really well because they can be leaving groups. They can also be protecting groups. So they can protect an alcohol from reactivity, okay, which we'll see again at the end of this chapter. They'll talk about those protecting groups. What did we say about protecting groups? We don't really deal with them because we could just look them up. We end up doing a lot of waste chemicals, okay? But if you see some abbreviations, MS, TF, TS, that's what they're referencing is those larger structures behind them, okay? And so sometimes they do show up primarily as protecting groups, okay? With that, we'll go ahead and end. Yeah, because we don't want to start that one.